Alright, in this video we'll be going through rotational motion. This is very similar to circular motion. However, instead of something rotating in a circular path, instead we have something that is rotating on its own axis. And to start this discussion, we can start with a little bit of a conundrum, we can say. Let's say if we have a ball at the top of a hill, right? And then as this ball rolls down, we should be able to find its velocity, right? Because we have EP up here, so max EP, and then we have max EK down here. So this is max, and then this is also max, right? So max EP at the top, and then max EK at the bottom. And so simply we should be able to go EP is equal to EK, and therefore mgh is equal to half mv squared, and then we solve for v, and we should be able to find its velocity. However, when we do carry out this calculation, our velocity is lower than expected. Right? So the question is, why is this? Well, our first thought may be that some of the energy is lost to friction and heat, and you'll be correct, that is the case. However, even if we correct for this energy loss, the velocity is still lower than expected. So why is this? Well, it turns out that most of the energy lost in this scenario is lost due to rotation. As the ball moves down the slope, it is rolling as well as moving translationally, right? So as the ball rolls down, we can say it has an angular velocity. I'll touch more on that, what that is later, right? So what we really should say is that the EP at the top translates into EK at the bottom, right? And this is translational, right? And translational just means forwards, right? Linear, if you will. But it also gets converted into EK rotational at the bottom, okay? A lot of subscripts there. And this is rotational motion, right? Okay, so it's going in a circle. Now, something we'll be using a lot in rotational motion is the idea of a radian. Okay, so we should know from maths or some other courses that this is an angle, right? So just like degrees, it's a type of unit for an angle. So by definition, 1 radian is the angle at the center of a circle when the arc length, which we can denote as S, is equal to the radius, which we can denote as little r. Okay? So what that essentially is saying is if we have a circle and we take some angle, let's say this angle right here, theta, theta is equal to 1 radian when this distance r is equal to this distance s. So when the arc length is equal to the radius. And so mathematically we can go that theta is equal to s over r. Now in your formula sheet you should have something like d is equal to r theta. This is pretty much the exact same equation. The d in this case is replacing s, which as you can see, s is a distance, so same difference, really. And obviously, these equations are just rearranged differently. Okay? Sweet. So now that we got that out the way, we can go through some of our rotational quantities. So on the one hand, we can note down our translational quantities, right? And then we can give our rotational equivalent on this side. So our first quantity is our distance, and that is in meters. So that's our translational version. And our rotational equivalent of that is theta, and that is in radians. And that is basically what we talked about up here. Okay? And if you really want, you can change that s to a d. Okay? Next up, we have our velocity, and that's obviously in meters per second. And our rotational equivalent of that is our omega, or our angular velocity, and that's in radians per second. And just a note on angular velocity and why this quantity is important. if we take a spinning plate, right? So this is a top-down view of a bird's eye view of a spinning plate. And so the plate is spinning right there. If we have an object on the outside, and then we also have another object closer to the center, these objects are obviously going to spin around the circle like so, okay? Now, just like translational velocity, our velocity is equal to distance over time, or the change in distance over the change in time, right? So same with angular velocity, it's the same thing. We have our angular velocity is equal to the change in our rotational distance, which is our angle, all over the change in time. So as you can see, let's say our objects have moved over here, right? So they're still in line. You can see that the angle that they turn is the exact same. It's the exact same theta value. They're still in line with each other as they move across. However, this distance is shorter compared to this distance, right? The arc length for this inner object is smaller than the arc length for the outer object. And so the outer object had to cover more distance. And so as it covers more distance, its velocity, its translational velocity must be larger. And so if we have two objects on the plate at different radii, their translational velocities are going to be different. However, the angular velocity is the same. Now we have this equation for our angular velocity. However, on your formula sheet, you have probably seen something like omega is equal to v over r, or the rearranged version of v is equal to r omega, right? So how do we get these equations, okay? As we know, if we differentiate displacement, we get velocity, and if we differentiate velocity, we get acceleration. That is no different for our rotational equivalents, right? If we differentiate angular displacement, which is our theta, we get our angular velocity. So if we were to rearrange this equation, so we get d is equal to r theta, right? And we differentiate both sides with respect to time. So differentiating both sides with respect to time, we get d over dt, right? The reason why I put this in brackets is so it makes it easier to see because they're both d's. Probably should have used this equation with the s, so it's a bit easier to differentiate, but oh well. And that's equal to r d theta all over dt, right? So we differentiate both sides with respect to t. So as I said before, if we differentiate our distance, we get our velocity, right? So that's velocity is equal to r, and if we differentiate our angular displacement, we get our angular velocity and we get r omega, right? And so that is where this equation comes from, okay? And obviously this is just a rearranged version. Our next quantity is our acceleration, and that's obviously in meters per second. And our rotational equivalent of that is our alpha, which is angular acceleration, and that's in radians per second. And we know our acceleration equation is a is equal to change in velocity over change in time. And so same thing on this side, we get our alpha is equal to the change in angular velocity over just change in time. Also, we have our alpha is equal to a over r, or our a is equal to alpha r. These equations are obviously the same equation, just rearranged differently, and they come about in the similar manner that this equation comes about, right? If we take this equation right here, and we differentiate on both sides with respect to time, dou. Like so, if we differentiate our velocity with respect to time, we get acceleration, and if we differentiate our angular velocity with respect to time, we get our alpha, which is our angular acceleration. And so therefore we get the same equation. Right, so that is all our translational quantities with their rotational equivalent. Right, so as you can see, from all these equations, right, this one, and this one, you can see that if we want to get the rotational equivalent of a translational quantity, we can just simply divide by the radius. And so now that I've shown you how these equations come about in the test or in any working you can do, now that you know how these come about, you can just simply take the shortcut of just dividing by the radius to get the rotational equivalent, right? So that's a neat little trick or rule that you can apply. Now, just like our quantities have rotational equivalents, our kinematic equations also have rotational equivalents. Right, so we know our acceleration is equal to the change in velocity over the change in time, and therefore we can rewrite this change in velocity as VF minus VI, and so we get A is equal to VF minus VI all over our T, and so therefore AT is equal to VF minus VI, and therefore AT plus VI is equal to VF. Now, this should look familiar as a kinematic equation, and we also do have a rotational equivalent of this. In order to get our rotational equivalent, we just simply replace all the translational quantities with their rotational equivalents, okay? So, first, our acceleration, the rotational equivalent of that is our alpha. There is no rotational equivalent of time because time is time. And so we get alpha t plus vi, what is the rotational equivalent of velocity? That's omega I, right? Omega initially, angular acceleration initially, is equal to our angular acceleration finally. Right, we also have Vf squared is equal to Vi squared plus 2AD, and therefore the rotational equivalent of that is omega F squared is equal to omega I squared plus 2 alpha theta. We also have D is equal to VIT plus half AT squared, and therefore the rotational equivalent of this is theta is equal to omega I t plus half alpha t squared, right? And therefore finally we have our distance is equal to VF plus VI all over 2 times our time, and therefore the rotational equivalent of that is theta is equal to omega F plus omega I all over 2 times our time, again because time doesn't have a rotational equivalent. Alright, so those are our rotational equivalent of our kinematic equations that we were familiar with from last year. Okay, now the typical scenario that you would see these rotational kinematics be used is when we have a flywheel situation and we have a mass that is attached via a rope to the flywheel, alright, and it's hanging off, and this mass is accelerating downwards with a constant acceleration, okay? And so therefore, because the flywheel has a axis of rotation over here, and the force is being applied at the center, there is going to be a torque produced, and therefore the flywheel is going to rotate with an angular velocity. Now, usually in level 3, the angular acceleration is constant, and so therefore we can use our kinematic equations above here. Because as you should know, you can only use kinematic equations when the acceleration is constant. And if you didn't know that, now you know. If you go to university, do some engineering or whatever, you will see some situations where you will deal with acceleration that is non-constant. But for now, level 3, you don't have to worry about that. Usually, I think all the time, the acceleration is always constant. So that's a typical scenario that you will see. There's plenty of examples in exams. I think in the 2024 exam, which I did, there is this exact scenario, and we use a kinematic to solve for its angular velocity as well. You may also see something like where we have a graph, and we have a situation like this, and we have an area under the graph, okay? And this is our omega, and this is our t. So our omega is obviously in radians per second, and our t is in time, so that's in seconds, right? This gradient right here is obviously the change in angular velocity over time, right? And so the change in angular velocity over time is equal to our angular acceleration, right? Again, stated this before, if we differentiate angular velocity, we get angular acceleration, and we know if we differentiate a line, we get its gradient. That's from like level 2. We also should know, level 3 calculus, that if we integrate something, we get the area under the graph. And if we were to integrate, let's see, where is it? If we were to integrate angular velocity, we should go backwards, if you will, backwards, and we get our angular displacement, which is our theta. And so the area under the graph is equal to our theta omega t, right? All right, so now that we got that out the way, we can move on to some problems now. So let's start off with question 1. And for this question, we have a situation where we have a record player, you know, those, old school record players where they have that music disc thing. And this music disc is rotating this way in a circle, okay? this record player is also rotating at 45 revolutions per minute, right? 45 RPM. And from here, we want to calculate its angular velocity, right? Calculate its angular velocity. The crux of this problem is that angular velocity is measured in radians per second. However, RPM is measured in revolutions per minute, right? Because that's what RPM stands for, revolutions per minute. And so we need to convert revolutions per minute into radians per second. So the first obvious difference between radians per second and revolutions per minute is that radians per second is measured in seconds and revolutions per minute is measured in minutes. So we need to convert RPM into seconds, right? So convert RPM into RPS, from revolutions per minute to revolutions per second. Because we know there are 60 seconds in 1 minute, if we have 45 revolutions per minute, we can divide this value by 60 to get our revolutions per second, right? So now that we've got it in terms of seconds, the other obvious difference is that radians per second is measured in terms of radians. However, this is in terms of revolutions. We should know that in one full revolution of a circle, there are 2 pi radians. So that means in one revolution, there are 2 pi radians. So in order to convert the revolutions into radians, we can times this value by 2 pi. And this gives us 3/2 pi radians per second, or 4.71 radians per second. There we go. So that is how you convert from RPM into radians per second. This is a pretty common merit level problem, or it would be an intermediate step in an excellence level question. So it's a pretty important skill for rotational motion in NCEA Level 3. So now one more question. Moving on to question 2. A flywheel rotates at 45 radians per second and undergoes an angular acceleration of 2 radians per second. And this all happens in 5 seconds. Calculate its final angular speed and how many radians it traveled through during this time. So in order to solve this question, we would need to use our kinematic equations, which we found earlier. The way we would solve these problems is very, very similar to how we would solve level 2 kinematic questions. Because all the kinematic equations are essentially the exact same equation, just rearranged differently, and they use different variables. In order to solve these problems, all we need to do is look at the variables that we are given, or the values that we are given, and what value we're trying to solve for, and find out which kinematic equation is best suited for the job. So let's first start off with this first part right here. Let's call this part A, and we can call this part B. So let's start off with part A, right? We can put that over here. Let's have a look at what we are given. We're given an initial angular velocity, right? So our omega I is equal to 4 radians per second, right? We're also given an angular acceleration, so our alpha is equal to 2 radians per second. And we are also given a time of 5 seconds, right? So if we have a look at our kinematic equations, the best kinematic equation for the job is probably going to be this one, right? So our final angular velocity, which is what we are trying to find, which is equal to our initial angular velocity plus alpha t, right? So our final angular velocity is equal to omega I, which is our initial angular velocity, and that's a value of 4, plus our angular acceleration, which has a value of 2 radians per second, times our time, which has a value of 5 seconds, right? And that means 4 plus 2 times 5 is 10. And so 4 plus 10 is 14 radians per second. There we go. And that is our omega finally. Now, moving on to part B, we want to find how many radians it has traveled through. So let's look at our kinematic equations again. So as you can see, we have 2 equations right here, which are rearranged for theta. And we also have a third kinematic equation right here that also uses theta. However, for this one, you would have to rearrange for theta in order to use it. Now, in my demonstration, I'm going to use all 3 of these kinematic equations, which use theta within them, to show you that these kinematic equations are the exact same equations, just rearranged slightly differently and use different variables. And all 3 of these equations should give us an answer of 45 radians. Alright, so let's solve these. So I've just copied and pasted these over. So let's start off with this first equation right here. As I said previously, we need to rearrange to find this one. And so we can rearrange for our theta, and we'll get omega finally squared minus omega initially squared over 2 alpha. That's equal to our theta. And so plugging in our numbers, our final angular velocity is 14, so 14 squared, minus our initial angular velocity, which is 4 squared, all over our 2 times our angular acceleration, which was 2 radians per second. And plugging that into our calculator, we get a value of 45 radians. Right? And so for this equation right here, our theta is equal to our initial angular velocity. And so we know that's 4 times our time, which was 5 seconds, plus half times our angular acceleration, which was 2 radians per second, times our time squared, which was 5 seconds. And plugging that into our calculator, we indeed get a value of 45 radians. And our last equation right here, we have our theta is equal to our final angular velocity of 14 plus our initial angular velocity of 4 all over 2 times our time of 5 seconds. And this indeed gives us a value of 45 radians. So as you can see, all our kinematic equations gave the correct answer. Now, in an exam, you don't have to use all kinematic equations. Again, I just did that for demonstration purposes, like I said before. However, which kinematic equation would I use in an exam? The kinematic equation that I would use in the exam is this one right here. The reason for that is because that is the only kinematic out of all these three that doesn't use our final angular velocity. The reason why I don't want to use our final angular velocity if this was an exam is because if we had gotten this value wrong, then that doesn't affect our second part of the equation, right? So if we got the first part of the equation wrong, we still have a chance of getting the second part right. However, if we got the first part wrong, and then we use one of these two equations, which use our final angular velocity of 14, we would also get the second part wrong, which is not what we want. We want to have the best chance to get all the questions correct, right? So yes, and in an exam situation, I would use this, but just know that is only because we calculated our angular velocity first initially in this question. All right, so that is all it for part 1.